In this video, we're going to talk about conjugate addition reactions and finish it up with a Robinson annulation. So, in the aldol reaction, remember what you can do is take an aldehyde and condense it with itself to get an alpha-beta unsaturated aldehyde or ketone. In this video, we're going to talk about really interesting reactions of these unsaturated species. What's interesting about alpha-beta unsaturated ketones and aldehydes is that all aldehydes and ketones possess a resonance structure that separates the charges, negative charge on oxygen, positive charge on carbon. But the difference is if you have an unsaturated ketone or aldehyde, you have this double bond next door, which we can then draw a third resonance structure, right, that places the positive charge on the beta carbon. So notice that if we combine all these resonance structures together, we get a partial positive charge on this carbon, a partial negative on this oxygen, which we've always seen for all reactions of ketones and aldehydes. But since we have this third resonance structure, then not only is this carbon electrophilic, but also the beta carbon of alpha-beta unsaturated ketone or aldehyde can also be electrophilic. So what we're going to see is if I'm a nucleophile and I encounter an alpha-beta unsaturated aldehyde or ketone, I could attack here, or I could attack here. So this is the beta carbon. So we can see in some cases nucleophiles are going to attack here, in some cases nucleophiles are going to attack here. If we attack here, that's called conjugate addition, as we're going to see. And this all has to do with understanding the resonance structures and how they compile with one another to make a resonance hybrid. Okay, so this is our resonance hybrid. You can be electrophilic here or here. We're going to see some nucleophiles add here, some nucleophiles add here. And one way you can rationalize or talk about this is if we look at this entire pi system, right, from the oxygen all the way through to the beta carbon, we call this atom 1 and atom 2 and atom 3 and atom 4. If I'm a nucleophile and I add here, that's going to be called a 1,2 addition because we're going to get an O minus, which is eventually going to get protonated by the solvent. So we're going to add something to this oxygen and we're going to add something to this carbon like a Grignard reagent, as we're going to see on the next slide. If I'm a nucleophile and I add here, that's going to be called a 1,4 addition or a conjugate addition. Okay, so really strong bases. And mostly the only ones that we're going to talk about are Grignard reagents or lithium aluminum hydride. These undergo 1,2 additions, right? So the R group attacks this carbon. We break the carbon-oxygen double bond, which eventually gets protonated. So we added something to 1 and we added something to 2. That's a 1,2 addition. If we have a weaker nucleophile, remember cuprates aren't as reactive as Grignard reagents. Cuprates undergo a 1,4 addition. It's harder to see, right, because what it looks like is that we added across 3 and 4. But what happens is you have your R group, that adds here, this double bond moves over, and this double bond moves over. So what you have now is an enolate, right? Which gets protonated by acid. So initially, what you've generated is a product of 1,4 addition, right? You've added something to oxygen 1, you've added something to the beta carbon, which is 4. So that's why it's called a 1,4 addition, but remember now we get this tautomerization where we go from the enol back to the aldehyde, and thus what appears like a 3,4 addition is called a 1,4 addition for some reason. Long story short, I think the easiest thing or the most important thing to remember is that Grignard reagents or lithium and aluminum hydride add like we always see, whereas if you have an alpha beta unsaturated carbonyl compound, weaker bases, stabilized bases, will add to the beta carbon, so we get a new carbon-carbon bond here, which can be really useful. So, as I mentioned, 1,4 addition, the nucleophile like the cuprate is going to attack the beta carbon. This double bond moves over, this double bond moves over, we get an enolate. Enolates get protonated to form the enol, which rapidly tautomerizes. So this is why it's called a 1,4 addition. We have something added to 1 and 4. It appears as though something just added across the double bond. That's because this hydrogen moved through tautomerization from the oxygen down to the carbon. Okay, stabilized enolates. So we talked about cuprates. The biggest one is if we have a stabilized enolate, meaning that we have two carbonyls, right? A dicarbonyl compound is going to form a very stabilized enolate. If we treat it with potassium hydroxide, we're going to stoichiometrically, irreversibly, under non-equilibrating conditions, we get an enolate. That enolate, that stabilized enolate, will add to our alpha-beta unsaturated aldehyde through a process called a Michael addition. Conjugate addition, Michael addition, or 1,4 addition are all synonymous terms that pretty much mean the same thing. So we add to the beta carbon. This moves over here. This moves over here. So the result after step 2 right is we get this. Now we add acid. Acid protonates this oxygen, and then that enol undergoes tautomerization to give this product, right? And the net if we're just drawing the product, notice that what happened is this carbon, which is in between our two carbonyls of our stabilized enolate, attacks this carbon, and we lose our carbon-carbon double bond. So we form a new sigma bond between this carbon and this carbon at the expense of a pi bond. So this is a very thermodynamically favorable reaction known as the Michael addition or conjugate addition. So the terminology that's used a lot of times is that your stabilized enolate is going to be called your Michael donor in the Michael addition. This is donating the electrons. The beta carbon of our alpha beta unsaturated carbonyl compound, which has a partial positive charge in the resonance hybrid, it's electrophilic. That's going to be our Michael acceptor. So alpha beta unsaturated aldehydes and ketones make very good Michael acceptors. You have to have two carbon oxygen double bonds to get a good Michael donor, because you need this thing to be a very weak base, and you need this to be a very stabilized enolate to be a good Michael donor. So let's say you only had one carbon oxygen double bond. This guy is not a good Michael donor, so we can't do the same reaction that we did last time. For example, let's say we take this guy and we want to form the enolate under non-equilibrating conditions. We add LDA to deprotonate here. We could think that would Michael in to this Michael acceptor and then add acid. But the thing is, we don't obtain this product in good yields. The reaction just doesn't work that well. We need a different strategy if we want to obtain these kinds of products. And so instead of doing a Michael reaction, what we do instead is a process called the Stork Enamine synthesis. So remember that if you take a ketone with a secondary amine, like let's say dimethylamine, for example, and an acid catalyst, after step 1, what you're going to end up with is an enamine. And if you look at, so this is enamine that results from step 1. And the nice thing about enamines is that they have a resonance structure, an important resonance structure where we have a formal negative charge on the carbon and we have a formal positive charge on the nitrogen. So enamines are really nucleophilic at this carbon right here, and they make really good Michael donors. So I think I have this on the next slide here. So we already know the steps, we already know the mechanism for formation of an enamine. We just said enamines are really nucleophilic on this carbon. They make good Michael donors, right? So what can happen is these electrons kick down, our nucleophile adds in to 1,4 to our Michael acceptor. And if we draw the product here, we have an iminium ion, right? And an enolate. And then step 3, we add water or maybe dilute acid. Dilute acid is going to hydrolyze the iminium ion to a ketone. It's going to protonate our enolate to make it enol, which will tautomerize to a ketone. So this is the product of, and this is the trick that you use to turn a bad Michael donor into a good Michael donor. A good enamine being a good Michael donor. This enolate would not have been a good Michael donor, and so we don't use that. Instead, we use the enamine. The last reaction that we're going to talk about is a Robinson annulation. This is a really cool reaction, which looks intimidating. It's not really that complicated. If you take a Michael donor like this dicarbonyl compound and you treat it with a base like sodium hydroxide, right? First thing that's going to happen is we're going to form our enolate between the two carbonyls. This is a good Michael donor, so it's going to do a conjugate addition into our Michael acceptor. So the product is going to look like this, right? We have the methyl that was already on there. So this carbon is this one, and this carbon is this one, and this carbon is this one, and we have an O minus. And usually we do this with some aqueous solvent. So let's say it's water. Well, the enolate can get protonated. So now the product after the Michael addition is this guy, right? Which I've drawn differently here. Next, what happens is under those basic conditions, this thing can react further to do a Robinson annulation, noticing that we have an alpha position here, we have alpha hydrogens here, and we have alpha hydrogens here. If we deprotonate these, we'd form a 1, 2, 3, 4, 1, 2, 3, 4, so that's not going to work, but these alpha hydrogens can be removed under the basic conditions of the reaction to generate an enolate here. Now we can have a 1, 2, 3, 4, 5, 6 membered ring. So now we see intramolecular aldol reaction. We attack that carbon, we break the carbon-oxygen double bond, which gives us something that looks like this. 2, 6, O minus, double bond O, methyl. This is this carbon right here. This, under the aqueous conditions, can get protonated, and then this can undergo aldol condensation to give us the double bond between these two carbons. So the Robinson annulation is a combination of a Michael addition to generate this product, followed by aldol condensation. And notice that you can start with very simple starting materials and build up very complex ring systems that are common to steroids and other important molecules. Okay, summary. Conjugate addition is otherwise known as 1,4 addition. Resonance stabilized bases are usually these are weak bases. They're going to add to the beta carbon to give 1,4 addition products. Cuprates also do so, and enamines also add to the beta carbon. So what we're going to see is resonance highly stabilized enolates, cuprates, and enamines. These are also called Michael additions. But to be a good Michael donor, you have to have a 1,3 dicarbonyl to get that really stabilized enolate. When you're looking at Robinson annulation, first thing is don't be intimidated. It looks complicated, but we know all these reactions. We can just string them together to make these complicated molecules. It's just a Michael addition followed by an intramolecular aldol reaction. The trick to getting these reactions right is to always count your carbons.